In the quiet reaches of the universe, where light drifts for thousands of years before finding an eye to meet it, great clouds of gas and dust float in the darkness. They are delicate, immense, and ancient. Nebulae, the luminous birthplaces and final resting grounds of stars. These ethereal clouds trace the cycles of matter and energy that shape galaxies. To gaze at them is to look into the cosmic forge, where stars are born, where they die, and where the dust of those deaths becomes the seed of new creation. A nebula begins as little more than interstellar gas, mostly hydrogen and helium, spread thin across light years of space. At first glance, the void between stars seems empty, a perfect vacuum. But it is not. Even in the darkest regions, a few atoms linger in every cubic centimeter. Over millions of years, these atoms drift, collide, and sometimes gather in denser pockets. Gravity, though faint at first, slowly begins to pull on this material. Where the gas becomes just a little thicker, the pull becomes stronger, and the cloud starts to condense. From this slow dance of attraction, a nebula takes form. The interstellar medium is a dynamic ocean. Energy from nearby stars, supernova explosions, and galactic magnetic fields continually stir its contents. Ultraviolet radiation ionizes hydrogen atoms, stripping electrons from protons, creating vast glowing regions. Shock waves travel through the gas, compressing it into new shapes. Cosmic rays thread through the dust like invisible rain. Each of these processes contributes to the endless sculpting of nebulae. Each ripple, shock, and burst of light reshaping their fragile forms. Some nebulae are remnants of death. Others are cradles of life, or rather, of starlight. Astronomers categorize them into several broad families: emission nebulae, reflection nebulae, dark nebulae, planetary nebulae, and supernova remnants. Though these names seem distinct, in truth the boundaries blur. A single nebula may be both reflective and emissive, or evolve from one form into another as it changes and interacts with the surrounding galaxy. Emission nebulae shine with their own light. They are regions where young, massive stars emit intense ultraviolet radiation that excites the hydrogen gas around them. When those energized hydrogen atoms recombine, electrons falling back into orbit around protons, they release photons, typically in the vivid red of hydrogen alpha light. The result is a glowing cloud, radiant against the background of space. Some of the most famous nebulae belong to this category: the Orion Nebula, the Lagoon, the Eagle, the Rosette. These are the cosmic nurseries where new stars are born in clusters, surrounded by disks of dust that may someday form planets. Reflection nebulae, by contrast, do not emit their own light. Instead, they act as vast celestial mirrors, scattering the starlight that falls upon them. They often appear blue, because shorter wavelengths of light scatter more efficiently off small dust particles. The light we see from a reflection nebula is, in a sense, borrowed. It is the whisper of nearby stars caught and softened by interstellar dust. Light turned to mist. Dark nebulae are the opposite of both. They are not radiant, nor reflective, but opaque. They appear as shadows against the luminous background of the Milky Way, cold, dense clouds of molecular gas that block the starlight behind them. Inside these dark regions, hidden from sight, gravity quietly works. Over time, knots within the cloud collapse, heating up as they shrink, forming the first hints of new stars. When these stars ignite, they illuminate the material around them, and the once dark nebula blooms into light. In this way, darkness becomes the source of radiance. Planetary nebulae are something else entirely. Despite their name, they have nothing to do with planets. The term is an artifact of early astronomy, when observers peering through small telescopes saw faint, round disks that resembled the planets of our solar system. In reality, these are the dying shells of medium-sized stars, like our Sun will someday become. When such a star exhausts the hydrogen in its core, it expands into a red giant. Its outer layers grow unstable and are eventually blown into space, creating an expanding sphere of gas. The hot, exposed core left behind, a white dwarf, emits ultraviolet light that causes the ejected gas to glow. For tens of thousands of years, the nebula shines, before gradually fading into the interstellar medium once more. And then there are the supernova remnants, the colossal remains of stars that died in violent explosions. When a massive star collapses under its own gravity, it releases an enormous shockwave that tears its outer layers apart, sending them hurtling into space at thousands of kilometers per second. These expanding shells sweep up surrounding gas, creating complex, filamentary nebulae like the Crab Nebula or the Veil Nebula. Within them, particles are accelerated to near light speeds, and the energy released can outshine entire galaxies for a brief moment in time. In these fiery ends, the universe scatters the heavy elements forged in the star's core: carbon, oxygen, iron, gold, seeding the cosmos with the building blocks of planets and life. Each of these nebula types tells a story about transformation. A star's birth and death are not endpoints, but phases in an endless circulation of matter. The atoms that compose your body, carbon in your cells, oxygen in your lungs, iron in your blood, were once part of some ancient nebula, perhaps born from the death of a star billions of years ago. Through that cycle, the universe recycles itself, weaving new worlds from old dust. To study nebulae is to study the interplay of light and matter, the physics of ionization, radiation, and fluid motion on vast scales. Astronomers use many tools to unravel their secrets. Optical telescopes reveal glowing filaments and clouds in visible light, but much of a nebula's structure is hidden in wavelengths invisible to the human eye. Infrared telescopes peer through dust to reveal the warm cocoons of forming stars. Radio telescopes detect the faint emissions of molecules such as carbon monoxide, tracing the cold gas where stars gestate. X-ray observatories capture the hot, violent regions around supernova remnants, where temperatures reach millions of degrees. Together, these instruments build a multi-wavelength portrait of the cosmos, each band of light adding a new layer of understanding. The Orion Nebula, just visible to the naked eye as a faint smudge in Orion's sword, is one of the most studied regions in the sky. It lies about 1,300 light-years away, part of a larger complex of gas and dust that stretches across the constellation. Within it, thousands of young stars are forming. The brightest region is powered by a cluster of massive, hot stars known as the trapezium. Their radiation ionizes the surrounding hydrogen, producing the nebula's brilliant glow. Observations show protoplanetary disks, tiny, flattened clouds of gas and dust, around many of these young stars, suggesting that planetary systems are forming even now, in the heart of the cloud. Elsewhere, the Eagle Nebula captures the imagination with its towering columns of gas and dust, famously imaged by the Hubble Space Telescope as the pillars of creation. These pillars are several light-years tall, sculpted by the intense radiation from nearby young stars. At their tips, new stars continue to form, each a small beacon in the mist. What appears serene from afar is in fact a turbulent environment. Winds, radiation, and shock waves shaping the clouds in an intricate balance of destruction and creation. The physics that governs these vast formations is the same that shapes the smallest structures of matter. Gas pressure, gravity, magnetic fields, and radiation all interact in complex ways. Within molecular clouds, the coldest, densest type of nebula, temperatures can drop to just a few degrees above absolute zero. At such low temperatures, hydrogen atoms bond into molecules, and heavier molecules such as ammonia, water, and methane also form. These molecular clouds can be hundreds of light years across and contain enough material to form thousands of stars. Yet they remain mostly invisible, detectable only through their faint radio emissions. Inside them, turbulence creates knots and filaments, the precursors of star-forming cores. As each core collapses, it spins, drawing in material from its surroundings. Eventually, the central temperature rises until nuclear fusion begins, hydrogen fusing into helium, and a new star is born. The light of this young star then begins to erode the cloud that formed it, dispersing the gas into space. The nebula dissolves, and the cycle begins anew. On galactic scales, nebulae trace the structure of spiral arms, glowing where waves of density have compressed interstellar gas. In the Milky Way, the Orion Arm, the Sagittarius Arm, and others aligned with these bright patches of star formation. The same patterns appear in distant galaxies observed by the James Webb Space Telescope, where knots of emission mark clusters of young, hot stars. Everywhere we look, from the nearby Magellanic Clouds to the far-flung spiral galaxies hundreds of millions of light-years away, we see the same story written in light and dust. Clouds condensing, stars igniting, radiation sculpting the gas into new forms. The study of nebulae also reveals the chemistry of the cosmos. Spectroscopy, analyzing the light from these clouds, allows scientists to determine their composition. By spreading the light into its component wavelengths, astronomers can identify specific emission lines corresponding to elements like hydrogen, helium, oxygen, nitrogen, and sulfur. These patterns act like fingerprints, telling us not only what the nebula contains, but also its temperature, density, and motion. Through these measurements, we learn how galaxies evolve, how elements are distributed, and how the interstellar medium changes over time. In recent years, high-resolution data from observatories such as the Atacama Large Millimeter Array, ALMA, and the James Webb Space Telescope have deepened this understanding. They show the intricate web of filaments and cavities within nebulae, revealing that their beauty is not merely aesthetic, but structural, a record of the forces shaping the universe. Shock waves from dying stars carve bubbles into the gas. Magnetic fields twist and guide the flow of matter. Jets from newborn stars pierce their surroundings, creating streaks of glowing material known as Herbig-Haro objects. Each feature is a clue, a piece of a grand story told across billions of years. The light we see from a nebula is ancient. The Orion Nebula's glow that reaches our eyes tonight left its source around the time humans were building the earliest civilizations. The light from the Crab Nebula began its journey when Chinese astronomers recorded a guest star in the year 1054. In each case, we see not the nebula as it is, but as it was, frozen in time. The universe, vast as it is, offers us these glimpses, moments preserved in light. In their silent glow, nebulae remind us that creation and destruction are two sides of the same cosmic process. The death of one star enriches the universe with the materials needed for the birth of another. Dust formed in the cooling shells of dying stars drifts through space, merging with gas to form new clouds. Within those clouds, new stars and planets will arise, and perhaps one day, life will look back upon the stars and wonder where it came from. Even in their stillness, these clouds are never at rest. Over millions of years, they evolve, expanding, dispersing, recombining. Their beauty lies not only in their colors or shapes, but in what they represent: continuity amid change, order within chaos. The universe itself breathes through them. As we look deeper into the cosmos, the line between observation and imagination softens. A nebula is real, measurable, physical. Yet its forms invite wonder, even reverie. To drift among these clouds in thought is to float through time, through the fabric of cosmic memory. Each photon we receive carries not only information but history, a memory of a moment long past, written in light. The pace of cosmic evolution is slow beyond comprehension, yet here, in these glowing clouds, we see it captured in form. What is light to us is energy transforming matter, gravity sculpting dust, the universe writing itself in color and shadow. And so, the study of nebulae becomes not just a scientific pursuit, but a meditation on existence itself, on beginnings, endings, and the endless continuity between them. Deep within the veils of cosmic mist, where light grows faint and temperatures fall to near absolute zero, the story of star formation unfolds in silence. Nebulae are not still clouds but living systems, their structures shaped by gravity, turbulence, and time. They are the breathing tissue of galaxies, forming and dispersing in cycles that span millions of years. Within the cold, molecular depths, the raw ingredients of light itself are born. A nebula begins as an interstellar cloud, composed mostly of hydrogen molecules with traces of helium, carbon, oxygen, and heavier elements. Though vast in scale, spanning tens or hundreds of light years, these clouds are tenuous. A single cubic centimeter may contain only a few thousand atoms, far emptier than the best vacuum we can produce on Earth. Yet within that apparent emptiness lies the potential for everything we see in the night sky. Gravity, the slow sculptor, works patiently upon this diffuse material, gathering it into denser knots and filaments. The process begins with instability. Over time, certain regions of a molecular cloud become slightly denser, perhaps due to a passing shock wave from a nearby supernova, or the pressure of radiation from massive stars. These small differences set gravity into motion. As the density increases, the region cools, allowing molecules to radiate away energy. The cooler it becomes, the less it resists collapse. Gradually, a core forms, an invisible heart of the nebula, drawing in gas and dust from its surroundings. Inside these cores, gravity competes with other forces. Thermal pressure, magnetic fields, and turbulent motion all resist collapse. The balance between these forces determines how and where stars are born. Astronomers model these dynamics with simulations that span thousands of years of cosmic time, tracing the flow of gas through intricate webs of filaments. What they find is a universe of self-organization, patterns emerging spontaneously from chaos. The result is a hierarchical structure, from vast molecular complexes down to small, dense clumps where individual stars ignite. At the center of a collapsing core, density and temperature rise until nuclear fusion becomes possible. Hydrogen atoms fuse into helium, releasing enormous amounts of energy. The young protostar stabilizes, and its radiation begins to push back against the infalling material. This marks the transition from a dark, hidden phase to a visible one. The surrounding dust glows in infrared light, heated by the newborn star. Jets of gas stream outward along the star's magnetic poles, carving tunnels through the surrounding nebula. These outflows regulate the star's growth, carrying away excess angular momentum and shaping the environment around it. Eventually, the protostar emerges fully into the light, illuminating its birthplace. The radiation from massive, hot stars ionizes the nearby hydrogen, creating bright emission nebulae. The regions between these glowing zones remain dark, harboring cold gas yet to be touched by starlight. Over time, the radiation pressure and stellar winds disperse the nebula, revealing the new star cluster within. The cloud that once nurtured them fades back into the interstellar medium, leaving only traces, filaments of gas, pockets of dust, the lingering echoes of creation. This process, though described in stages, is continuous and overlapping. In large nebula complexes, such as the Carina Nebula or the Cygnus X region, thousands of stars form over millions of years, each generation influencing the next. The most massive stars live fast and die young, exploding as supernovae that compress nearby gas and trigger new waves of star formation. Thus, one generation's death becomes the seed of another's birth. This chain reaction sustains the evolution of galaxies, ensuring that the light of the universe never truly fades. To understand the life cycle of nebulae, astronomers study their composition in exquisite detail. Within molecular clouds, the chemistry is complex and surprisingly rich. Observations reveal the presence of more than 200 different molecules, water, carbon monoxide, ammonia, formaldehyde, methanol, and even simple organic compounds like amino acid precursors. These molecules form on the surfaces of dust grains, where atoms stick, meet, and bond in the icy darkness. Ultraviolet light and cosmic rays trigger further reactions, creating new species. When the cloud warms during star formation, these molecules evaporate into the gas phase, releasing their chemical stories into space. Dust plays a crucial role in this cosmic alchemy. Though it makes up only about 1% of a nebula's mass, it is vital to its behavior. Dust grains absorb and scatter light, shielding the interior of the cloud from harsh radiation. They provide surfaces for chemical reactions, helping molecules form. They also influence the thermal balance of the gas, cooling it efficiently by re-emitting absorbed energy as infrared radiation. Without dust, the dense, cold environments required for star formation could not exist. The dust itself originates from the remnants of earlier stars, material forged in stellar furnaces and expelled into space by winds and explosions. Every particle drifting through a nebula carries with it the memory of older suns. When we look at images of nebulae captured by telescopes like Hubble or Webb, we see this process frozen in time. The glowing tendrils, sculpted edges, and dark silhouettes all trace the boundaries between radiation and shadow, between destruction and creation. The vibrant colors in these images correspond to specific wavelengths of light emitted by different elements: red for hydrogen, green for oxygen, blue for sulfur or nitrogen. Yet what appears vividly painted to our eyes is in reality invisible to the human spectrum. These colors are translations, a language of light made visible so that we may perceive what our eyes alone cannot. Each nebula tells its own story. In the Carina Nebula, about 7,500 light-years away, massive stars blast their surroundings with ultraviolet radiation, carving vast cavities and pillars of dust. The turbulence and pressure create new pockets of star formation. In the Lagoon Nebula, 4,000 light-years away, a similar interplay occurs. Winds from young stars sculpting the gas into rippling forms. In the Tarantula Nebula, within the Large Magellanic Cloud, an immense cluster known as R136 hosts some of the most massive stars known, each hundreds of times the mass of the Sun. Their collective energy dominates the surrounding gas, making this one of the most luminous star-forming regions in the local universe. But not all nebulae are nurseries. Some are graveyards. The death of a massive star is among the most transformative events in the cosmos. When its core collapses, the star releases a flood of energy, briefly outshining entire galaxies. The resulting supernova explosion tears apart the star's outer layers, producing shock waves that race outward into space. These shocks compress the surrounding gas, heating it to millions of degrees and causing it to glow in X-rays. The expanding shell forms a supernova remnant, rich in heavy elements forged in the dying star's heart. Over thousands of years, the remnant cools and merges with the interstellar medium, enriching it with new material that will one day form planets and life. One of the best-studied remnants is the Crab Nebula, the aftermath of a supernova observed on Earth in the year 1054. At its center lies a neutron star, a dense core only about 20 kilometers across but containing more mass than the Sun. This neutron star spins rapidly, emitting beams of radiation that sweep through space like a cosmic lighthouse. The energy from this pulsar powers the surrounding nebula, producing intricate filaments and glowing regions. Observations across radio, optical, and X-ray wavelengths reveal a complex interplay of magnetic fields and relativistic particles, a dynamic system still evolving nearly 1,000 years after the explosion. Another example, the Veil Nebula in the constellation Cygnus, shows the aftermath of a supernova that occurred about 10,000 years ago. Its delicate, thread-like structures trace the shock front as it expands into the interstellar medium. The colors correspond to different elements: oxygen glowing blue-green, hydrogen red. Despite its beauty, what we see is the echo of destruction, the visible ghost of a star that once shone brightly in our galaxy. In contrast to these explosive endings, the deaths of sun-like stars are quieter, yet equally profound. As such a star nears the end of its life, it expands into a red giant, shedding its outer layers into space. The core contracts into a white dwarf, while the expelled gas forms a planetary nebula, a luminous shell glowing from the ultraviolet light of the dying star. The resulting patterns can be breathtakingly symmetrical. Rings, bubbles, and intricate shapes sculpted by magnetic fields and stellar winds. Planetary nebulae such as the Helix, the Cat's Eye, and the Ring Nebula offer glimpses of our own sun's distant future. In about 5 billion years, it too will cast off its outer layers, briefly creating a glowing nebula before fading into a white dwarf. Each phase of this life cycle, birth, radiance, death, feeds into the next. The gas and dust expelled by dying stars drift through the galaxy, eventually gathering again into new molecular clouds. Within those clouds, new stars form, and with them, new planets. The same carbon that once floated in the atmosphere of a red giant may one day be part of a living organism. This recycling of matter is the heartbeat of the cosmos, a process that has been ongoing for more than 13 billion years. Nebulae also shape the large-scale evolution of galaxies. Star formation is not evenly distributed. It occurs in bursts, triggered by interactions between clouds, or by the gravitational influence of nearby galaxies. When galaxies collide, tidal forces compress the interstellar gas, igniting waves of star formation that light up vast regions of space. In such starburst galaxies, nebulae become the engines of transformation, their light tracing the cosmic rhythms of creation. In our own Milky Way, regions like Orion, Carina, and Cygnus are active nurseries. They remind us that the galaxy is not static but alive, a dynamic system constantly renewing itself. Over time, as stars form and die, the composition of the interstellar medium changes. Heavier elements accumulate, making each generation of stars richer in metals than the last. This gradual enrichment is why planets like Earth, with its complex chemistry, could exist at all. The nebulae that came before us sowed the elements that became oceans, air, and life. To observe a nebula is to observe time itself stretched across space. The light from the Eagle Nebula's pillars of creation, for example, began its journey about 6,500 years ago. Some scientists believe the region may have already been disrupted by a nearby supernova since then, meaning that what we see is already gone, its beauty preserved only in the light still traveling toward us. In this way, the cosmos teaches us a gentle lesson about impermanence, that even the most magnificent structures fade, and that their fading is part of the same cycle that brings new light into being. In the quiet moments of observation, astronomers sometimes describe nebulae not as objects but as processes. They are the visible expressions of physics unfolding. Gravity compressing gas, radiation sculpting matter, turbulence weaving patterns of density and void. Every glowing filament is an equation made visible, every shadow a record of forces unseen. The beauty we perceive in these forms arises from the same laws that govern the simplest particles. In that sense, a nebula is not just a cloud of gas, it is the universe contemplating itself through light and matter. If one could drift through a nebula, the experience would be both sublime and subtle. Despite their immense size, these clouds are so diffuse that you would not feel their presence. There would be no solid walls of color, no fog to touch, only the faintest mist, illuminated from afar. The glowing regions we see in photographs would appear dim to the human eye, as their light is spread thin over vast distances. Yet with sensitive instruments, we could trace the gentle currents of gas, the magnetic threads guiding dust, the silent interplay of forces that give rise to stars. In that stillness, surrounded by the faint hum of cosmic radiation, one might sense the vast continuity of all things, the slow breathing of the galaxy itself. In the end, nebulae remind us that the universe is not merely a collection of stars, but a living system of transformation. The clouds we observe are both memory and promise, memory of stars that once were, and promise of stars yet to come. Their light travels across eons to reach us, carrying the quiet message that creation never ceases, it only changes form. Between the stars, vast and unseen, lie the engines of transformation, the nebulae whose delicate forms connect the life of galaxies to the birth and death of light itself. To understand them is to trace the subtle choreography of matter and energy that governs the cosmos. These clouds, though ethereal, follow precise physical laws. They are shaped by pressure and magnetism, by radiation and gravity, by the balance of cooling and heating that determines whether they collapse to form stars or disperse into the void. Their beauty, though soft and dreamlike to our eyes, is the visible consequence of these invisible equations. At their core, nebulae are laboratories of physics. They are regions where gas dynamics, chemistry, and radiation intersect. The primary ingredient, hydrogen, exists in several forms: as neutral atomic gas, as ionized plasma, or as molecular hydrogen in the densest regions. Each state interacts differently with light and with magnetic fields, giving rise to the complex textures observed in nebulae. The cooler, molecular clouds are opaque in visible light but shine in the infrared and radio. The warmer, ionized regions glow in vivid reds and pinks, the signature of hydrogen recombination. Between them lies a thin, transitional layer known as the photodissociation region, where ultraviolet light from nearby stars breaks molecules apart and heats the gas. These layers, stacked like invisible veils, define the anatomy of a nebula. The interplay of forces within these regions determines a nebula's shape and fate. Gravity pulls inward, trying to gather the gas into dense clumps. Gas pressure pushes outward, resisting collapse. Magnetic fields thread through the cloud, channeling the flow of matter along invisible lines. Turbulence stirs the gas, creating eddies and filaments. Radiation from stars both illuminates and erodes the cloud, sculpting its surface into pillars, arcs, and globules. Every detail we see in a nebula's structure, the curves, the shadows, the rippling edges, is a frozen trace of these competing influences. The shapes are not random, they are signatures of physical processes unfolding on colossal scales. In recent years, high-resolution simulations and observations have begun to reveal this hidden architecture in astonishing detail. Using instruments such as ALMA and the James Webb Space Telescope, astronomers can now map the fine filaments of molecular gas within clouds, measuring their density, temperature, and motion. These filaments often align with magnetic fields, forming networks that resemble the branching of trees or the veins of a leaf. Along these threads, gravity gathers material into knots, future sites of star formation. The process resembles the condensation of dew along a web, delicate, distributed, and guided by underlying structure. Energy flow within nebulae is equally intricate. Ultraviolet radiation from massive stars ionizes the surrounding gas, heating it to thousands of degrees. The gas expands, driving shock fronts outward into the cooler material. These shocks compress the gas ahead of them, potentially triggering new star formation. Meanwhile, the expanding bubble created by the hot stars gradually grows, merging with others to form superbubbles, vast cavities within the galactic disk. Inside these cavities, the density is low, and the temperature can reach millions of degrees. They act as channels through which energy and matter circulate between the stars and the interstellar medium. Every phase of a nebula's existence is a step in this cosmic circulation. The gas that collapses to form a star will one day be returned to space through stellar winds and supernova explosions. The heavy elements produced in those stars will mix with the surrounding gas, altering its composition. Over billions of years, This cycle enriches galaxies, turning the simple hydrogen and helium of the early universe into the complex chemistry that makes life possible. The carbon in living cells, the oxygen in oceans, the calcium in bones, all were once atoms drifting in nebulae, waiting for gravity to bring them together again. The chemistry of nebulae is one of their most fascinating aspects. Within cold molecular clouds, where temperatures can fall below 10 Kelvin, reactions occur on the surfaces of dust grains coated with ice. Hydrogen atoms combine to form H2 molecules, the fundamental building block of dense clouds. Other atoms, oxygen, nitrogen, carbon, bond to form water, ammonia, methane, and methanol. More complex molecules, including organic compounds with carbon chains, arise from the interplay of cosmic rays and ultraviolet radiation. These molecules emit radiation at characteristic wavelengths, allowing astronomers to identify them through spectroscopy. The presence of such complexity in seemingly barren regions of space hints at the deep chemical continuity between stars, planets, and life. In warmer nebulae, ionization dominates the chemistry. The ultraviolet light from nearby stars strips electrons from atoms, creating plasma. As electrons recombine, they emit photons at specific wavelengths. The resulting emission lines, like fingerprints, reveal which elements are present and their relative abundances. Hydrogen produces its characteristic red glow. Oxygen and nitrogen add green and blue hues. Sulfur and helium contribute faint tints at the edges of the spectrum. By analyzing these lines, scientists can infer the temperature and density of the gas, the strength of the radiation field, and the speed of the gas along the line of sight. Each photon carries a piece of the nebula's story. Beyond the visual, nebulae radiate across the entire electromagnetic spectrum. In radio waves, astronomers detect cold hydrogen and carbon monoxide tracing the bulk of the molecular material. In infrared light, they see the heat from warm dust grains and protostars hidden from view. In X-rays, they observe the high-energy regions near supernova remnants and stellar winds. This multi-wavelength approach transforms our understanding from a static picture into a dynamic, living system, one that evolves and breeds across time. The scale of these structures is difficult to comprehend. The Orion Nebula alone spans about 24 light-years across. The Carina Nebula stretches more than 200. Some molecular complexes, such as the Taurus or Perseus clouds, extend for hundreds of light-years, containing enough mass to form thousands of suns. Yet within these grand scales, the processes that shape them operate on microscopic interactions, collisions between individual particles, magnetic alignments within dust grains, quantum transitions within atoms. The grandeur of nebulae lies in this bridge between the infinitesimal and the infinite. The way small-scale physics gives rise to large-scale beauty. Galaxies themselves depend on these processes. In spiral galaxies like our Milky Way, nebulae trace the arms like glowing threads. The density waves that move through the disk compress the gas, triggering star formation in rhythmic patterns. The resulting clusters of young, luminous stars light up the gas around them, creating vast emission regions visible across millions of light-years. These star-forming regions are the markers of galactic vitality, the signatures of ongoing creation. In elliptical galaxies, where the gas has largely been exhausted or expelled, nebulae are rare. Their absence speaks of an older, quieter cosmos, one in which the cycle of renewal has slowed. Even beyond galaxies, in the vast spaces between them, nebula-like structures exist. The intergalactic medium, though thin, contains filaments of gas that connect galaxies across cosmic distances. Observations and simulations suggest that the universe itself is web-like, with galaxies strung along threads of hydrogen stretching for millions of light-years. These immense filaments are the faint echoes of the same processes that govern nebulae on smaller scales. Gravity shaping gas into structure, radiation illuminating it, time weaving complexity from simplicity. Within all these scales, the dance of matter follows a universal rhythm: condensation, illumination, dispersal, renewal. It is the rhythm of the cosmos itself. To study nebulae is to hear this rhythm in light, to trace the breathing of galaxies as they create and dissolve their luminous clouds. When astronomers map the distribution of nebulae across the sky, they are effectively mapping the life cycle of the universe's energy. How it moves, how it transforms, how it continues. There is something profoundly meditative about this. The physics, precise and quantifiable, reveals not cold machinery but an unfolding harmony. Each equation describing gas flow, each spectrum of light, each faint radio signal contributes to a larger narrative, that of a universe continually creating and recreating itself. The nebulae we see are not isolated phenomena but expressions of that continuity, moments in an infinite story written across time. And as our telescopes grow more powerful, our vision of these clouds deepens. The James Webb Space Telescope, observing in infrared, has revealed layers of structure once hidden by dust. In the Pillars of Creation, it shows newly forming stars still wrapped in cocoons, their jets streaming into space like delicate threads of light. In the Tarantula Nebula, Webb's observations expose thousands of young stars previously unseen, their combined radiation shaping the surrounding gas into complex arcs and ridges. These views remind us that what appears still from afar is alive with motion, currents and flows unfolding over millennia. The light from these nebulae carries not only information but memory. It has traveled across space for thousands or millions of years, bearing the imprint of the moment it left its source. To look at the Orion Nebula tonight is to see light that began its journey long before the first cities on Earth rose from the plains. The photons that strike our eyes have crossed interstellar dust, magnetic fields, and cosmic voids to arrive here, tiny messengers from a time when the universe was younger. Each one carries with it a story of transformation, a whisper of creation. In the quiet of observation, this realization becomes almost dreamlike. The mind drifts outward with the light, imagining the vast distances it has crossed, the countless particles it has touched, the stillness of the spaces between. The nebula becomes more than an object of study. It becomes a mirror of time and consciousness, a reminder that we too are part of the same unfolding story. The atoms in our bodies once floated in such clouds, absorbed light from ancient stars, and drifted until gravity called them into new forms. To look at a nebula is, in a way, to look at our own origins suspended in the cosmic night. As the voice of the universe quiets into radio whispers and faint glows, the boundaries between science and wonder begin to dissolve. The data, the equations, the careful measurements, all reveal a truth both simple and profound. The universe is continuous, and everything within it is connected. Nebulae are the luminous bridges between matter and light, between past and future, between the physical and the contemplative. Their silent forms invite reflection, not just on how the cosmos works, but on what it means to be part of it. If you could drift now through one of these nebulae, through the calm interior of a molecular cloud, where light barely reaches, you would feel an immense serenity. The stars would be distant glimmers beyond the dust, their light filtered into soft hues. The gas around you would move slowly, almost imperceptibly, in great waves shaped by magnetic fields. Occasional flashes of ultraviolet light would spark at the edges, marking the birth of new stars far away. Time itself would seem to slow, the minutes stretching into centuries, the silence becoming the only sound. It would be less like traveling and more like dreaming, floating in the universe's own breath. And yet, every atom in that dream would be engaged in ceaseless motion, collisions, vibrations, the faint hum of energy exchange. The stillness is an illusion born of scale. On every level, creation continues. This quiet paradox, the coexistence of stillness and activity, of peace and transformation, is what gives nebulae their power over our imagination. They embody the rhythm of existence itself, the endless unfolding of form within formlessness. As we study them, we are not merely collecting data. We are, in a sense, listening to the universe's heartbeat. The frequencies of hydrogen, the glow of oxygen, the cold emission of dust, all are notes in a cosmic symphony that began with the Big Bang and continues through every nebula that drifts between the stars. To understand that music is to recognize our place within it, not apart from it, but as part of the same melody, carried on the same light. And so the science, when followed far enough, circles back to something quiet and timeless. The equations dissolve into awareness. The structures become a kind of cosmic art. The nebulae, those immense and gentle clouds, are not distant at all. They are the reflection of the same processes that gave rise to everything we know, everything we are. The dust that forms their soft veils is the same dust that forms us. The light that glows within them is the same light that burns in our stars and our minds. In this recognition, the voice of the cosmos becomes a lullaby, a slow, endless whisper of creation, change, and return. The nebula breathes, the galaxy turns, and the universe, ever so patiently, dreams itself forward. In the vastness of interstellar space, the life of a nebula begins almost invisibly. It starts with a whisper of atoms, hydrogen, helium, traces of carbon, oxygen, and silicon, drifting cold and thin between the stars. These atoms, remnants of ancient supernovae and stellar winds, float through the galactic disk for millions of years, mingling in diffuse clouds that are almost too tenuous to measure. In a single cubic centimeter of such a region, there may be only 1 or 2 atoms, less than the best vacuum we can create on Earth. Yet over galactic scales, those few atoms add up to immense oceans of gas and dust stretching for hundreds of light years. Where conditions allow, gravity begins to weave these atoms together. Subtle fluctuations in density, sometimes triggered by passing shockwaves from a nearby supernova, or the compression of a spiral arm's gravitational field, start to grow. The gas cools, losing energy as faint infrared radiation, and as it cools, it can collapse further. What begins as an almost imperceptible density variation becomes a gathering, a slow inward drift of matter that deepens with time. In these early stages, astronomers call them molecular clouds, for within the depths, hydrogen pairs off into molecules, and carbon and oxygen form simple compounds. The gas cools further, reaching just a few tens of degrees above absolute zero. These clouds, dark and opaque, can be hundreds of light years wide, containing enough material to form thousands of stars. Yet from the outside, they appear as silhouettes, dark nebulae blotting out the brighter starlight behind them. The Horsehead Nebula in Orion, the Coal Sack near the Southern Cross. These are among the most famous examples, dark clouds where starlight cannot yet penetrate. Inside such clouds, gravity's subtle hand continues its work. As regions within the cloud collapse, they fragment into smaller clumps. Within each clump, gravity grows stronger as mass concentrates and the core density rises. The balance between internal pressure and self-gravity tips, and a slow cascade begins. Clumps within clumps, each one potentially the seed of a new star. The process is slow, measured in millions of years, yet constant, an invisible architecture of collapse and gathering. When the core of one of these fragments becomes dense enough, it traps radiation that once escaped freely. Heat builds. At around 10,000 Kelvin, the pressure within the core holds the collapse for a moment, forming what astronomers call a protostar. The surrounding gas, still falling inward, forms a disk around this newborn center, a protoplanetary disk of dust and molecules. Here, the story of the nebula begins to diverge into new paths, one of stellar birth and one of planetary potential. The glow of these newborn stars begins to alter their surroundings. Radiation floods outward, ionizing the nearby gas, stripping electrons from atoms and causing them to shine. What was once a dark nebula becomes a bright one, an emission nebula. The Orion Nebula, visible even to the naked eye as a faint smudge beneath Orion's belt, is a textbook example. A stellar nursery, glowing pink and violet from the excitation of hydrogen and oxygen. Within it, stars only a few 100,000 years old are sculpting the gas that gave them life. Over time, the radiation and stellar winds from these hot, young stars push back against the surrounding cloud. They carve out cavities and blow away curtains of dust, creating intricate filaments and pillars. This sculpting is both destructive and creative. The compressed edges of these expanding bubbles can trigger new collapses, forming the next generation of stars. In this way, one wave of stellar birth can ignite another, propagating across a cloud in a slow cosmic chain reaction that lasts tens of millions of years. But stellar birth also brings stellar death. The most massive stars, burning through their fuel in just a few million years, end their lives as supernovae. Explosions so powerful they momentarily outshine entire galaxies. When such a supernova occurs within or near a nebula cloud, it blasts shockwaves into the gas, heating it to millions of degrees and spreading heavy elements far and wide. These elements, iron, nickel, calcium, carbon, enrich the cloud, seeding it with the building blocks for future planets and life. Supernova remnants like the Crab Nebula are the after-images of that violence, expanding shells of gas, energized by the remains of the collapsed star at their center. The Crab Nebula, born from a supernova observed in 1054 CE, still glows with the light of high-energy electrons spiraling through magnetic fields. Its filaments are composed of oxygen, sulfur, and hydrogen, materials that will one day drift outward to join the interstellar medium again. Through such cycles, nebulae both die and are reborn. The gas dispersed by a supernova eventually cools, merges with other clouds, and begins the long process of condensation again. Galaxies are therefore ecosystems of nebulae, each one feeding the next, recycling matter through billions of years. The Milky Way alone contains thousands of active star-forming regions, each at a different stage in this endless rhythm. Astronomers study these processes using many wavelengths of light, because each reveals a different layer of the story. In visible light, we see the bright, ionized hydrogen glowing red. In infrared, we can peer through the dust to the warm cocoons of newborn stars. In radio wavelengths, giant molecular clouds reveal their cold molecular hydrogen, carbon monoxide, and ammonia. And in X-rays, we see the hot, shocked gas left behind by supernova explosions. By combining these, we build a full picture of how nebulae live, breathe, and evolve. Modern telescopes have deepened this understanding. The Hubble Space Telescope captured the iconic pillars of creation, towering columns of gas and dust in the Eagle Nebula, showing how ultraviolet radiation from nearby stars is slowly eroding them. The James Webb Space Telescope, with its infrared eyes, now peers even deeper, revealing stars forming inside those pillars, wrapped in swirls of dusty gas invisible to previous instruments. Through such images, we see nebulae not as static objects but as dynamic, living landscapes, places where time, energy, and matter intertwine. In recent decades, astronomers have begun to map the flows of material within these regions. Observations show that molecular clouds are turbulent, filled with supersonic currents and magnetic fields that twist and fold the gas. These motions can both aid and resist star formation. Turbulence creates dense knots where collapse can begin, but also stirs the cloud, delaying its fragmentation. Understanding these balances remains one of astrophysics' great challenges. Chemical evolution within nebulae also fascinates researchers. Within the coldest parts of molecular clouds, simple molecules adhere to dust grains, forming icy mantles. Cosmic rays and ultraviolet light trigger chemical reactions on these surfaces, creating more complex compounds, formaldehyde, methanol, and even amino acid precursors. Thus, nebulae are not just the birthplaces of stars, but laboratories for prebiotic chemistry. The same molecules detected in interstellar space are later found in comets and meteorites, hinting at the continuity between nebular chemistry and the origins of life. As the star formation cycle continues, some nebulae transform into planetary nebulae, a misnomer born from early astronomers who mistook them for distant planets. These are not related to planet formation, but rather to stellar endings. When a star like the Sun exhausts its hydrogen and helium, it expands into a red giant and eventually sheds its outer layers. The exposed core, now a white dwarf, radiates intense ultraviolet light that causes the ejected gas to glow in soft blues, greens, and reds. The Ring Nebula in Lyra, the Helix Nebula in Aquarius. These are delicate, short-lived sculptures of dying stars. Over tens of thousands of years, their gas disperses, enriching the interstellar medium once more. In this constant interplay, formation, illumination, dispersal, nebulae embody the circular rhythm of cosmic life. Every atom in our bodies has passed through this cycle many times. The oxygen we breathe, the iron in our blood, the calcium in our bones, all were once part of nebulae, born in the hearts of stars, scattered by explosions, then drawn back together by gravity. The scale of these processes can be hard to grasp. The Orion molecular cloud complex, for instance, stretches across hundreds of light years and contains enough gas to form tens of thousands of suns. Within it, astronomers identify filaments, long, thread-like structures of gas and dust where density is highest. These filaments act as the veins of the nebula, channeling material toward its densest cores. Observations by instruments like the Herschel Space Observatory reveal that these filaments have a nearly universal width of about 0.3 light years, a mystery that hints at underlying physical laws governing their formation. Gravity, turbulence, and magnetic fields all play roles. The balance between them determines whether a nebula forms stars efficiently or remains quiescent. Some regions, like the Taurus molecular cloud, produce stars slowly and sparsely. Others, like the Carina Nebula, erupt in waves of rapid star formation, lighting up the sky with young, massive clusters. The reasons for this diversity are still being explored, but they likely involve the interplay between large-scale galactic dynamics and local feedback from previous generations of stars. In galaxies beyond our own, we see these same cycles playing out. 29 The Large Magellanic Cloud hosts the Tarantula Nebula, one of the most active star-forming regions in the local group. Here, the massive cluster R136 produces intense radiation and stellar winds that sculpt the surrounding gas into a web of filaments. The entire region spans nearly 1,000 light-years, a miniature galaxy of creation within a satellite galaxy. Observing such regions helps astronomers understand how star formation scales up from local clouds to entire galactic systems. Across cosmic time, nebulae have played a central role in shaping the appearance of galaxies. In the early universe, after the first stars formed, their radiation ionized the surrounding hydrogen, clearing away the primordial fog. This epoch of ionization ended the cosmic dark ages, making the universe transparent to light. The same processes continue today on smaller scales. Nebulae around young clusters re-ionize pockets of interstellar gas, creating the glowing bubbles that decorate spiral arms. Eventually, the most energetic stars and supernovae disperse their natal clouds completely. What remains is a cluster of new stars, shining in the clear air of interstellar space, surrounded by the faint residues of the nebula that birthed them. The Pleiades in Taurus, for example, are a cluster of young stars moving through a thin veil of reflection nebulosity, a final echo of the dust that once surrounded them. Over millions of years, even that dust will drift away, leaving only the stars. The transformation from dense cloud to open cluster marks the end of a nebula's active life. Yet its material is never truly gone. Galactic rotation, stellar winds, and supernovae distribute the gas, enriching the interstellar medium for future cycles. Astronomers call this process galactic ecology, the continuous recycling of matter through stars, nebulae, and back again. As we contemplate this cycle, we begin to sense the rhythm of time on a cosmic scale. What seems static in human life, a nebula fixed in the sky, is actually fleeting in galactic terms. In tens of millions of years, it will have changed completely. Stars born, stars died, gas dispersed, new clouds formed elsewhere. The night sky is a snapshot of these vast, ongoing transformations, frozen for a moment in our view. Even now, instruments are tracing these flows of matter across the Milky Way. The Gaia mission, mapping the positions and motions of over 1 billion stars, reveals streams of young stars tracing back to their nebular origins. Combined with radio surveys of hydrogen gas, we can see how spiral arms act as conveyor belts of creation, compressing gas as they pass, triggering star formation, then leaving behind the dispersed remnants. Nebulae, then, are both the cradles and the ghosts of stars. They mark the places where gravity and radiation meet, where energy transforms matter, where the universe writes and rewrites its story in gas and light. Their beauty lies not only in their colors and shapes, but in what they represent, the continual renewal of creation itself. The Milky Way, seen edge-on from afar, would appear as a river of light encircling the dark. Woven within it, countless nebulae trace its arms like threads of silver mist. Each spiral arm is not a solid structure, but a pattern, a density wave that moves through the galactic disk much like ripples in water. As the wave passes through, gas and dust are compressed, cooling and forming molecular clouds, which in turn become nebulae and new stars. When the wave has moved on, the newly formed stars drift away, leaving behind the next wave to repeat the cycle. Through this rhythm, nebulae act as the breathing of a galaxy. They inhale diffuse gas and exhale newborn stars. Observations in the radio and infrared show this relationship clearly. Giant molecular clouds cluster along the leading edges of spiral arms, while bright emission nebulae, the glowing hydrogen regions, form slightly behind, where stars have just been born. By tracing their positions, astronomers can even map the speed at which spiral density waves travel through the galaxy, roughly 20 kilometers per second, a slow tide on a cosmic scale. The magnetic field of the galaxy threads through all of this. Invisible to the eye, it shapes the motion of charged particles and subtly guides the structure of nebulae. Polarization studies, measurements of how light is oriented after passing through dust, reveal that magnetic lines often run parallel to filaments in molecular clouds. These fields can provide support against gravitational collapse, delaying star formation until local conditions overcome that resistance. In regions where magnetic tension is weak or where turbulence disrupts it, collapse proceeds more easily, forming clusters of new suns. In this way, nebulae are sculpted not only by gravity and radiation, but also by the unseen hand of magnetism. The delicate threads we see in images, wisps curling and branching like veins in a leaf, are often magnetic structures traced in gas. They give nebulae the graceful, filamentary appearance, as if painted by invisible lines of force. Galactic rotation also contributes to their shape and fate. As clouds orbit the center of the Milky Way, differential rotation, the fact that inner parts move faster than outer parts, stretches them out, twisting them into elongated forms. Over tens of millions of years, these shearing motions can disperse a nebula entirely, blending its gas back into the wider interstellar medium. Yet before that happens, star formation within it may have already created clusters that continue on their own paths, slowly dispersing across the galactic disk. Astronomers observe similar behavior in other galaxies. In the nearby spiral M33, for example, vast arcs of emission nebulae trace the spiral arms like glowing pearls. The largest of these, NGC 604, spans more than 1,500 light-years and contains hundreds of massive young stars. In ultraviolet light, they blaze fiercely, ionizing the surrounding hydrogen and sculpting the cloud into a cavernous bubble. This interplay between stellar radiation and nebula gas, repeated countless times, defines the luminous pattern of a spiral galaxy. Feedback, the influence of young stars on their natal clouds, is a key theme in nebula science. When a cluster forms, its brightest members emit torrents of ultraviolet light and powerful stellar winds. These winds create expanding shells that sweep up gas into dense ridges. Along those ridges, gravity may trigger further collapse, forming the next generation of stars. But feedback can also quench star formation by dispersing the remaining gas too quickly. Whether a nebula continues to form stars or fades into dispersal depends on the delicate balance between compression and evacuation. Modern simulations model these interactions in detail. Using supercomputers, astrophysicists recreate clouds of gas under the influence of gravity, radiation, and magnetic fields. They can watch virtual nebulae form, swirl, and fragment over millions of simulated years. What they find is a self-regulating system. Too much star formation leads to strong feedback that halts further collapse. Too little allows gravity to dominate again. The result is a galactic equilibrium, where nebulae convert only a few % of their gas into stars before being disrupted. This inefficiency is what keeps galaxies from exhausting their gas too quickly, allowing them to continue forming stars for billions of years. Between active star-forming regions lie the interarm zones, quieter stretches of the galaxy filled with diffuse gas and faint, extended nebulae. Here, the ultraviolet light from distant stars slowly ionizes hydrogen, creating what astronomers call the warm ionized medium. It glows weakly in the red light of the hydrogen alpha line, giving the Milky Way its soft, diffuse background. These interarm regions are the resting phases of nebula life, the long intervals between bursts of formation. Beyond the visible disk, high above the galactic plane, faint clouds of gas drift through the halo. Some are remnants of ancient supernovae, others are infalling streams of material from smaller satellite galaxies. When such clouds encounter the disk, they can reignite nebular activity by injecting fresh gas into the star-forming cycle. The galaxy, in this sense, feeds itself through slow rainfalls of interstellar matter, maintaining its nebular reservoirs over cosmic time. Even galaxies themselves can be considered as immense nebulous systems. In early epochs of the universe, when galaxies were younger and more gas-rich, enormous clumps of star-forming nebulae dominated their structure. Observations from the James Webb Space Telescope show these galaxies as turbulent, glowing webs of hydrogen and dust, cosmic nurseries on scales dwarfing anything seen today. Over billions of years, star formation consumed and dispersed much of that gas, leaving behind the more settled spiral and elliptical forms we see in the nearby universe. Inside these galaxies, nebulae continue to shape evolution. In starburst galaxies, where star formation occurs at a furious rate, overlapping supernovae and winds create galactic superbubbles, cavities tens of thousands of light-years across. The hot gas within them can escape into intergalactic space, carrying heavy elements outward. This outflow enriches the vast cosmic web, ensuring that future generations of galaxies inherit the chemical diversity needed for complex chemistry and, ultimately, for life. The colors we associate with nebulae, crimson, sapphire, emerald, arise from atomic transitions within the gases. Each element emits light at characteristic wavelengths when excited by radiation. Hydrogen produces the familiar red hydrogen alpha glow. Oxygen contributes blue-green hues. Nitrogen adds deeper reds. Astronomers use these emissions to measure the composition, temperature, and density of nebula gas. Through spectroscopy, a nebula becomes not just a picture, but a dataset, a record of the physical laws unfolding in real time across light-years of space. Dust, too, plays a central role. Though it makes up only about 1% of a nebula's mass, dust determines much of its appearance. Tiny grains of silicate and carbon, often coated with ices, scatter and absorb starlight. In reflection nebulae like that around the star Merope in the Pleiades, blue light dominates because shorter wavelengths scatter more efficiently. In darker regions, dust absorbs nearly all light, turning the nebula into a silhouette against the Milky Way's bright background. By studying how light is dimmed and reddened as it passes through these regions, astronomers infer the size and composition of the grains, and by extension, the processes that formed them. Dust grains also serve as the seeds of future planets. In protoplanetary disks around young stars, microscopic particles collide and stick, gradually forming pebbles, planetesimals, and eventually full-sized worlds. The dust seen in nebulae today may thus be the raw material of tomorrow's planetary systems. When we gaze upon the delicate blue haze of a reflection nebula, we are looking at the earliest ingredients of worlds not yet born. Across the galaxy, the life expectancy of a nebula depends on its environment. In dense spiral arms, where interactions are frequent, molecular clouds may collapse and disperse within 20 to 30 million years. In quieter outer regions, clouds can persist far longer, drifting undisturbed through the galactic outskirts. Some may even leave the disk entirely, carried by supernova-driven outflows into the halo, where they cool and eventually fall back again. This slow circulation, from disk to halo and back, is known as the galactic fountain. It keeps the Milky Way's gas supply in motion, recycling material between generations of stars and nebulae. The study of this circulation has advanced through radio observations of hydrogen's 21-centimeter line. This faint emission arises when the spins of hydrogen's proton and electron flip relative to each other. It is weak, but pervasive, allowing astronomers to map neutral hydrogen throughout the galaxy. Combined with measurements of ionized and molecular gas, these maps reveal the full cycle of nebular evolution. Cold clouds condensing into stars, hot gas rising from supernovae, and cool material raining back down. The result is a portrait of the Milky Way as a vast, self-sustaining ecosystem. As our understanding deepens, so too does our sense of connection. The gas that forms a nebula today will, in time, become stars, planets, and perhaps living beings. Every stage, collapse, illumination, dispersal, is part of a continuum that spans billions of years. To contemplate nebulae is to witness the slow, patient artistry of the cosmos at work. Even in their destruction, nebulae create beauty. When multiple supernova remnants overlap, their shockwaves interact to form intricate networks of filaments. The Cygnus Loop, a vast remnant of an ancient explosion, stretches across the sky as the Veil Nebula, delicate threads of red and blue marking the expanding shell of gas. Each filament glows as the shock front passes through, heating and ionizing atoms before cooling again. These remnants fade over tens of thousands of years, yet during that time they seed the interstellar medium with new heavy elements and magnetic energy, enriching the galactic tapestry. Through all of this, one principle remains constant. Energy flows outward, matter cycles inward, and structure emerges from the balance between them. Nebulae are where the universe expresses that balance most visibly. They are both the symptoms and the sources of change, intermediaries between the death of one generation of stars and the birth of the next. As we look at them through telescopes or images sent from orbit, we often forget that their shapes are transient. The luminous arches, knots, and veils we admire are moving, evolving, dissipating. In 100,000 years, the pillars of creation will be gone, eroded into wisps by the light of nearby stars. Yet other pillars will rise elsewhere, new clouds will condense, and the pattern will continue. The cosmos never truly ends or begins. It flows, continuously reshaping itself. When we understand this, the sight of a nebula becomes more than aesthetic. It becomes a reminder of persistence, of transformation as a natural law. Every glow in the night sky, every faint smear of color in long-exposure photographs, is evidence of creation in progress. And within those clouds, invisible to us now, are the beginnings of stories that will unfold across future eons. In the vast expanse of the interstellar medium, the final stages of a nebula's life unfold with quiet grandeur. The same cosmic forces that once gave it form now begin to undo it. Over millions of years, the intricate filaments, clumps, and cavities that once defined its structure are eroded by radiation pressure, stellar winds, and galactic shear. What remains is not the end of creation, but the quiet return of matter to its wider galactic context, a process that ensures the continuity of chemical evolution across cosmic time. Every nebula, whether emission, reflection, dark, or planetary, is a transient phase in the complex ecology of galaxies. These clouds represent the dynamic interchange between stars and the medium that surrounds them. They are formed, shaped, and ultimately dispersed by stellar evolution, leaving behind diffuse gas and dust that seed the next cycle of star formation. The process of dispersal is as important as that of creation. Without it, the interstellar medium would stagnate, and galaxies would eventually lose the ability to form new stars. The first step in nebula dispersal usually begins within the hot cores of massive stars that the nebula helped to create. Once these stars ignite, their ultraviolet radiation ionizes nearby hydrogen, forming H2 regions, vast, glowing bubbles of plasma that expand outward. Over time, these ionized fronts eat away at the neutral material of the surrounding nebula. The interface between ionized and neutral gas becomes a turbulent region, rich in shock waves and magnetic instabilities. As radiation pressure pushes outward, and thermal pressure within the H2 region increases, the expanding front sweeps up gas and dust into dense shells and filaments. In regions like the Orion Nebula, astronomers have observed these fronts advancing at speeds of several kilometers per second, gradually hollowing out the original molecular cloud. As the H2 region expands, it can trigger new episodes of star formation along its edges, a process known as collect and collapse. Yet as time passes, the intense energy output of the young, massive stars begins to dominate the balance. Stellar winds, continuous outflows of charged particles, combine with radiation pressure to blow cavities in the nebula, eventually dispersing the remaining material into space. Stellar winds play a major role in this phase. The kinetic energy they carry can exceed 10 to the power of 36 ergs per second, and when combined with the effects of radiation, they shape the nebula into complex shells and pillars. These winds are supersonic, often reaching velocities of hundreds or even thousands of kilometers per second. As they collide with denser regions of gas, shock fronts form, heating the gas to millions of degrees and emitting X-rays detectable by observatories like Chandra. Over time, these winds carve the nebula into sculpted forms, arches, filaments, and hollow bubbles, before dispersing the material altogether. In more evolved systems, such as planetary nebulae, dispersal is driven primarily by the aging central star. As a star similar to the Sun nears the end of its life, it expands into a red giant, shedding its outer layers through slow winds. Later, as the stellar core contracts and heats, a much faster wind, with speeds of up to 1,000 kilometers per second, overtakes the earlier, slower material. The collision between these two winds forms a thin, dense shell that glows as it absorbs ultraviolet photons from the hot core, now a white dwarf. Eventually, this shell continues to expand and dissipate into the surrounding interstellar medium, losing density and fading into invisibility. The physics governing this process can be described through hydrodynamic and magnetohydrodynamic (MHD) equations that couple fluid motion, radiation transport, and magnetic fields. The density gradients and magnetic field lines within the nebula determine the morphology of its dispersal. Where magnetic pressure dominates, gas flows are constrained along field lines, forming narrow filaments and jets. In contrast, in regions where thermal pressure exceeds magnetic influence, the expansion is more isotropic and rapid. Observations from the ALMA radio array have revealed that magnetic fields often align with the longest filaments in molecular clouds, guiding the dispersal process and influencing how turbulence decays. Turbulence itself plays a critical role in shaping the late stages of a nebula. Initially sustained by gravitational collapse and feedback from newly formed stars, turbulence decays over time as the energy sources weaken. When the driving forces cease, the internal motions subside, and the cloud begins to fragment into smaller clumps or dissolve entirely. The dissipation of turbulence leads to a more uniform pressure distribution, allowing gas to escape into the surrounding interstellar environment. Molecular lines observed in CO and other traces provide insights into the velocities and densities during these transitions, revealing a gradual smoothing of motion as the nebula fades. Galactic dynamics also contribute to dispersal. As a nebula orbits the galactic center, it encounters differential rotation. The inner parts of the galaxy move faster than the outer ones. This shear stretches and distorts the cloud over tens of millions of years. Gravitational interactions with spiral arms further perturb the structure. When a molecular cloud crosses a spiral arm, shock compression may briefly reignite star formation, but as it exits the arm, tidal forces and radiation fields strip away the remaining gas. This cyclical pattern ensures that nebulae are never static. They are continually reshaped by the broader galactic environment. Supernova explosions accelerate the final dispersal of nebulae. When one of the massive stars born within a nebula reaches the end of its life, it releases an enormous amount of energy, about 10 to the power of 51 ergs, in a matter of seconds. The resulting shock wave races outward at thousands of kilometers per second, sweeping up gas, dust, and magnetic fields. Initially, this shock compresses nearby regions, sometimes triggering further star formation, but as it expands, it tears through the remaining cloud, destroying molecules and dispersing dust grains. The enriched elements produced by the supernova, oxygen, carbon, silicon, iron, are injected into the interstellar medium, altering its composition and setting the stage for new stars with heavier elements. This recycling of material is a central feature of galactic evolution. Over billions of years, the gas content of a galaxy evolves through a balance between star formation and feedback processes like those just described. Nebulae are the visible intermediaries of this balance, the transitional phases where gas is concentrated, transformed, and then released again. Observations of nearby galaxies such as the Large Magellanic Cloud reveal entire networks of nebulae in different stages of formation and dispersal, illustrating this continuous cycle. Some regions glow brightly with active star formation. Others are faint remnants of once luminous clouds, now returning to the diffuse medium. The dispersal process has significant implications for galactic chemistry. As nebulae dissolve, they release dust grains and molecules that have been processed by radiation and shock waves. These grains often contain silicates, carbon compounds, and even simple ices, the raw ingredients for planets and life. Infrared spectroscopy from telescopes such as Spitzer and JWST has revealed complex organic molecules like polycyclic aromatic hydrocarbons, PAHs, in these regions, suggesting that even as nebulae fade, they contribute chemically rich material to the galaxy. Radiation transfer during dispersal also plays a key role in determining the appearance and lifetime of nebulae. As density decreases, photons can escape more easily, altering the ionization balance. The recombination of hydrogen, for instance, emits characteristic spectral lines such as H-alpha at 656. 3 nanometers, which astronomers use to trace the fading emission. Over time, as recombination outpaces ionization, the nebula's brightness diminishes. In the ultraviolet and X-ray bands, the emission fades even more rapidly, marking the transition from an active, ionized cloud to a neutral, invisible one. The timescales for complete dispersal vary widely. For planetary nebulae, the visible phase typically lasts only 10,000 to 50,000 years before expansion lowers the density enough for the gas to become transparent. In contrast, giant molecular clouds can persist for tens of millions of years before feedback and galactic shear destroy them. The difference lies in mass and scale. Molecular clouds can span hundreds of light years and contain up to 1 million solar masses of material, while planetary nebulae are small and relatively light. Yet in both cases, the ultimate fate is the same: the reintegration of material into the galactic medium. As the nebula fades, its dust grains continue to drift through the galaxy, subject to electromagnetic forces and radiation pressure. Some of these grains are incorporated into new star-forming regions, while others survive for hundreds of millions of years in the diffuse interstellar medium. Studies of interstellar extinction, the dimming of starlight by dust, show that even a tiny fraction of this material, when spread over vast distances, has measurable effects on how we perceive galaxies. Thus, the remnants of long-vanished nebulae subtly influence our view of the cosmos. Modern simulations allow scientists to model these processes in extraordinary detail. Using supercomputers, researchers can follow the evolution of a nebula from formation to dispersal, incorporating gravity, turbulence, chemistry, and radiation. These models reproduce the observed structures of real nebulae, from the bubble-like shapes of H2 regions to the filamentary webs of molecular clouds. They also reveal the delicate balance of forces required for a nebula to exist. Too much feedback, and the cloud disperses before stars can form. Too little, and it collapses entirely, leading to rapid, inefficient star formation. The equilibrium between these extremes sustains the long-term evolution of galaxies. Ultimately, the dispersal of nebulae is an act of renewal. Though the luminous forms we see through telescopes eventually fade, their matter is not lost. It becomes part of the diffuse gas that fills the galaxy, a mixture of atomic and molecular hydrogen, helium, and trace elements. Over time, this gas cools, condenses, and gathers once more into new nebular clouds. The same atoms that once glowed in an emission nebula may one day form part of a planet, or the atmosphere of a distant world. In this way, the dispersal of nebulae represents the continuity of cosmic matter. Every stage, formation, evolution, and dissolution, is linked in an unbroken chain of transformation. Stars form, live, and die, returning their enriched material to space, from which new stars are born again. This cycle has persisted for more than 13 billion years, shaping the structure and composition of the universe we observe today. As Part 4C draws to a close, we stand at the threshold between science and reflection, the point where physical processes and human wonder converge. The next phase, Part 5, will carry this scientific understanding into a quieter, more contemplative realm, tracing how the fading light of nebulae mirrors the ongoing renewal of the cosmos itself, the endless rhythm of creation, dispersal, and rebirth written across the stars. In the quiet reaches of the universe, where light drifts for thousands of years before meeting another particle, the story of nebulae continues. What once began as clouds of hydrogen and dust now expands, glows, and dissolves, revealing to us the slow rhythm of matter through space and time. Modern astronomy, equipped with instruments of extraordinary precision, now observes these transformations in exquisite detail. The James Webb Space Telescope, launched into its orbit beyond the Moon's shadow, has become humanity's most sensitive eye on the cosmos. In infrared wavelengths, it peers through curtains of dust that once hid the birthplaces of stars. Within the Carina Nebula, Webb's detectors have revealed thousands of previously unseen protostars, tiny points of infrared light cocooned in thick pillars of gas. These are systems only a few 100,000 years old, their light traveling across 7,500 light-years to reach us. Each one marks a continuation of the processes that began billions of years ago: gravitational collapse, nuclear ignition, and the slow sculpting of light and matter. The detail is astonishing. Where earlier telescopes saw only diffuse glows, Webb reveals structure, filaments, ripples, cavities, and fine dust columns illuminated by scattered starlight. In some regions, astronomers can trace how radiation from newborn stars erodes the very clouds that formed them. It's a paradox of creation. As stars ignite, their ultraviolet light strips away the gas around them, ending the cycle that gave them birth. Yet this very disruption creates new waves of compression that can spark more stars nearby. The universe thrives on such balances: destruction and renewal, dissolution and genesis, bound together in one unbroken flow. Other telescopes add layers to this cosmic portrait. The Atacama Large Millimeter, Submillimeter Array, ALMA, in Chile measures the faint glow of cold molecules within nebulae. It maps carbon monoxide, formaldehyde, methanol, and even prebiotic molecules, the building blocks of organic chemistry. In the Orion Molecular Cloud Complex, ALMA has traced the delicate filigree of gas that winds through the region, showing where dense cores collapse under gravity to form new stars. Some of these filaments are less than a light-year wide, yet stretch for tens of light years, forming a network of cosmic arteries through which matter flows. These molecular observations remind us that nebulae are not merely beautiful, they are laboratories of chemistry on a galactic scale. Within their coldest pockets, temperatures drop to only 10 or 20 Kelvin, where carbon and oxygen atoms freeze onto dust grains and combine into simple molecules. Over time, ultraviolet light or cosmic rays transform these ices into more complex compounds: amino acids, alcohols, even sugars. 46 here. When these grains are later incorporated into new planetary systems, they carry the seeds of organic chemistry to fresh worlds. Every cloud we observe may be the birthplace not only of stars, but of future biochemistry. In the Eagle Nebula, Webb and Hubble together have revealed towering columns of gas known as the pillars of creation. These columns are dense enough to resist the radiation winds of nearby stars, allowing new stars to gestate within their shadows. Recent infrared images show tiny jets of hydrogen streaming from their tips, signs of infant stars clearing away their envelopes. The heat of this feedback sculpts the columns into changing forms, and in a few million years they will be gone, their material dispersed into the galaxy. Even here, in one of the universe's most photogenic structures, impermanence reigns. Observations in the X-ray spectrum by the Chandra X-ray Observatory reveal yet another layer of reality. Within the same regions, hot plasmas millions of degrees in temperature fill the cavities between cold filaments. These X-rays trace shock fronts from stellar winds and supernova remnants. In the Rosette Nebula, Chandra detected an interior bubble of gas heated by massive O-type stars, its pressure driving an outward expansion that will eventually clear the entire region. What we see as tranquil beauty is, in truth, a dynamic balance of forces: gravity pulling inward, radiation and gas pressure pushing outward, turbulence weaving them together. Nebulae are thus not static backdrops, but evolving systems. Their shapes, densities, and colors record the dialogue between stars and their environments. By studying the light they emit, astronomers can reconstruct the physics within them. The spectral lines of hydrogen, helium, oxygen, and sulfur reveal temperature, composition, and motion. With modern instruments, even tiny shifts in these lines betray the velocity of gas clouds, often tens of kilometers per second, allowing scientists to map how material flows across light years of distance. Recent surveys show that nebulae are interconnected parts of larger galactic networks. The Milky Way's spiral arms are threaded with massive molecular complexes stretching hundreds of light years, the scaffolding upon which galaxies continually rebuild themselves. Each of these complexes hosts multiple generations of nebulae at different stages of evolution: cold, dense clouds, bright emission regions, dark, opaque lanes of dust. and the fading remnants of planetary nebulae and supernova shells. The picture is one of constant motion, an ecosystem of matter recycling itself over cosmic timescales. In this grand cycle, the boundary between one nebula and the next is often blurred. What we classify as the Orion Nebula is in reality just one luminous pocket within a far larger molecular cloud complex. Even as its brightest region glows in visible light, surrounding it are vast cold zones invisible to the human eye, reservoirs of gas that will one day form new stars. Observations from the Planck satellite have mapped the faint emission from these cold regions across the sky, revealing that the Milky Way is threaded by diffuse filaments of dust at every scale. The night sky, even where it seems empty, is full of faint whispers of light from nebulae too distant or too diffuse to see directly. Our galaxy contains hundreds of billions of solar masses of such gas and dust. And yet, at any moment, only a small fraction is condensed into bright, visible nebulae. The rest lies in diffuse form, waiting. Over tens of millions of years, galactic rotation, gravitational perturbations, and shock waves from supernovae gather this diffuse material again into new clouds. In the process, the chemistry evolves. Elements forged in stars are mixed and diluted, setting the stage for the next wave of creation. The entire galaxy breathes, its luminous nebulae flickering like slow heartbeats across epochs. Some of the most revealing data now come from JWST's mid-infrared instrument, MIRI, which captures the heat emitted by dust grains as small as a few microns. In these wavelengths, astronomers can detect polycyclic aromatic hydrocarbons, complex carbon molecules that emit distinctive patterns of light when warmed by nearby stars. These compounds are ubiquitous in nebulae, forming in the outflows of dying stars and spreading across interstellar space. The glow adds the faint orange and red hues seen in infrared images. Studying their distribution helps scientists understand how organic chemistry evolves between stellar generations, an unbroken thread from stardust to the molecules that may one day form living systems. As instruments improve, so does our sense of connection to the universe's cycles. Nebulae are now observed not only in our galaxy but in others, the large and small Magellanic Clouds, the Andromeda Galaxy, and beyond. Even at distances of millions of light years, the same patterns emerge: clouds of gas collapsing, stars igniting, radiation blowing cavities in the dust. The physics appears universal, governed by the same constants and the same laws of nature that operate here. It is humbling to realize that the principles unfolding across those distant galaxies are the same that once shaped the nebula that formed our own Sun, 4.6 billion years ago. Today, remnants of that ancient nebula are all around us. The interstellar dust that once glowed in infrared light now exists as minerals in meteorites, silicates in the Earth's crust, and carbon compounds in our own cells. The calcium in our bones and the oxygen we breathe were forged in the hearts of stars that once lived inside nebulae. Every glance through a telescope, every study of light from distant clouds, is also a glimpse backward, into the processes that made life possible. In recent years, the combination of data from JWST, ALMA, Chandra, and Gaia has allowed astronomers to simulate nebular evolution in unprecedented fidelity. These models follow the flow of gas from molecular filaments into protostars, the ignition of nuclear fusion, and the subsequent feedback that sculpts the surrounding medium. From these simulations emerges a deeper understanding. Nebulae are not mere side effects of star formation. They are the medium through which the universe organizes itself, converting chaos into structure. Even as the science deepens, there is something timeless about the way we respond to these clouds. Their colors, shapes, and patterns evoke the same awe they did for ancient observers who saw faint smudges in the sky without knowing what they were. The difference today is that we can decode their light, yet the wonder remains unchanged. As the data accumulates, a curious symmetry emerges between scale and stillness. The processes within nebulae are violent by human standards. supersonic winds, shock waves, radiation fields strong enough to strip atoms of electrons. Yet to our eyes, the motion is imperceptible. Across human lifetimes, the forms of these clouds barely change. The Eagle Nebula, the Carina, the Orion, they appear eternal, their transformations too slow for us to see. Only through generations of observation do we perceive the drift, the subtle expansion, the soft unraveling of filaments. This slowness invites a different kind of awareness. To observe a nebula is to step outside the human sense of time. We begin to sense the scale of processes that unfold not over years, but over eons. Radiation and gravity, working patiently, sculpt the cosmos grain by grain. Every glimmer of light from a nebula has traveled across centuries of darkness to reach our eyes. It is both ancient and immediate, a message from the ongoing story of the universe. Astronomers continue to study these clouds not only for their beauty but because they hold the key to understanding how galaxies evolve. The distribution of nebulae determines where new stars will form, which in turn influences the growth of planetary systems, the synthesis of heavy elements, and the structure of spiral arms. In computer models of galaxy formation, the physics of nebulae, their cooling rates, turbulence, and feedback, are among the most important parameters. The universe's large-scale structure, from filaments of dark matter down to the smallest clusters of stars, is shaped by the way gas behaves within these luminous clouds. Yet as the instruments record data, a parallel realization deepens. Even the most precise measurements cannot fully capture the silent majesty of these structures. Numbers and spectra tell us what they are made of, how they move, how hot or cold they are. But standing under the night sky, seeing a faint smear of light through a telescope, we also feel something beyond analysis. The awareness that we are watching a process older than memory, one that connects us to everything that has ever existed. In this sense, modern science and ancient wonder converge. The nebulae we study through infrared sensors are the same clouds that once inspired myth, poetry, and awe. We have changed the instruments of observation, but not the feeling itself. The universe continues to reveal itself slowly, softly, through clouds that glow and fade across millions of years. As Part 5a nears its close, the science quiets. The data remains steady and precise, but our focus begins to drift outward, beyond numbers and into presence. The light of the nebula travels through unimaginable distances, its photons scattered and absorbed, yet still they reach us. In their glow, we glimpse both the mechanism and the mystery of creation. And as the stars within these clouds continue to form, shine, and die, their energy and matter spread once again into the galaxy. Each cycle enriches the next. The same elements are used and reused, written into new configurations, new worlds, new beginnings. The nebulae teach us that nothing in the universe is truly lost, only transformed, dispersed, and reborn. In the quiet between observations, when telescopes rest and data streams fade into the silence of deep space, the cosmos continues its work. Gas flows, dust drifts, gravity gathers. The shapes change, the light evolves. The universe keeps breathing, slowly, endlessly. And somewhere, in that stillness, we can almost feel it, the rhythm of creation echoing through time. Across the darkness of the galaxy, the faint radiance of ionized hydrogen drifts like a whisper in an infinite cathedral. In some places it glows more brightly, the last visible signature of a once luminous star. JWST has mapped the filigree of such regions with astonishing clarity. Ripples of gas only a few light-years wide, shaped by ultraviolet photons that still stream outward from clusters of newborn suns. These observations, captured at infrared wavelengths invisible to human eyes, allow astronomers to follow how molecules reform in the cooling edges of these clouds. They reveal where oxygen, carbon, and nitrogen begin to combine again into the dust grains that will one day seed new worlds. When the Atacama Large Millimeter Array turns its many dishes toward these regions, it detects the faint rotational signatures of complex molecules. Methanol, formamide, acetylene, building blocks for chemistry that can one day lead to life. Each spectral line is a precise frequency, the telltale vibration of atoms bonded in the cold. In the soft hum of data streaming from the high desert of Chile, scientists hear echoes of creation repeating itself. Every molecule, every photon, carries the imprint of thermodynamic balance between chaos and order, energy and stillness. Far above the plane of the Milky Way, the Chandra X-ray Observatory watches the hotter side of this cycle. It sees remnants where nebulae have already been consumed, gas heated to millions of degrees by supernova shocks. The delicate balance of ionization and recombination dances at scales the human mind can scarcely hold. Yet these blazing clouds will, over millions of years, cool and merge again into the calm molecular reservoirs from which new nebulae will arise. Nothing in the universe truly vanishes, it only changes form. If we trace that exchange carefully, we begin to see the quiet unity that underlies all apparent motion. A star forms in the center of a dense nebula core, ignites fusion, and releases radiation. That radiation pushes outward, shaping the nebula into arcs and pillars. Eventually, the same star exhausts its hydrogen, swells, and dies, returning its outer layers to space. Those layers expand, mix with the interstellar medium, and later condense again. The same carbon that once glowed in a red giant's photosphere may now float as a microscopic crystal inside a dark cloud in Orion. And one day, perhaps, it will find itself part of a planet's crust, or within the body of a living being gazing back into the night sky. At the galactic scale, these exchanges form a rhythm. Radio telescopes trace threads of hydrogen weaving through spiral arms. The density waves that sculpt those arms act like vast cosmic metronomes, compressing gas in some regions while letting it disperse in others. Between the beats of that pattern lie the great, faint clouds, the diffuse nebulae that fill the majority of interstellar space. Their temperature is often just a few tens of kelvins above absolute zero. Yet within that near-frozen calm, the laws of physics continue to operate with quiet precision. Collisional excitation, radiative decay, magnetic alignment. Even in stillness, the universe hums with invisible activity. Astronomers measure the polarization of starlight to map those magnetic fields. The tiny, elongated dust grains within nebulae align with galactic magnetism, twisting the light that passes through them. The pattern tells researchers how energy flows within these clouds. It is a subtle code, a signature of turbulence and order coexisting. The fields are neither rigid nor chaotic, they guide matter while yielding to its motion. Like the currents in a deep ocean, they cannot be seen directly, only felt through their influence on what drifts within them. Slowly, through countless observations, a picture emerges of nebulae not as isolated ornaments but as continuous tissues within galaxies. They are the living membranes of the cosmos, permeable, ever-changing, connecting stars to stars. In some regions, gravitational forces pull gas into luminous knots. In others, radiation pressure scatters it apart. The balance between these forces defines the appearance of every nebula we see. The horsehead, the eagle, the lagoon, each is a momentary shape sculpted by light and time. As the data deepen, the imagination begins to slow. Numbers transform into images, images into impressions of vast stillness. One can almost sense the temperature gradients, the density waves, the long, slow rotation of a molecular complex around the galactic core. Over hundreds of millions of years, these motions carve subtle arcs through the disk of the Milky Way. The stars that will one day illuminate new nebulae are already drifting through those paths, their birthplaces predetermined by gravitational resonance and the inheritance of matter. When we look at the night sky, we are bathed in it, the afterglow of creation, faint but everywhere. It touches the skin, invisible but real, the softest possible reminder that we belong to all of it. Every moment, we are immersed in the same field that once shaped galaxies and dreams alike. As the thoughts drift further, the distinctions dissolve entirely. Science and wonder, knowledge and rest, merge like colors in a fading cloud. There is only motion, slow and eternal. The nebulae continue to live in that motion, glowing faintly at the edges of time, whispering the same story they have always told. That nothing is lost, that everything changes, that even the darkest space is full of light waiting to be seen. And somewhere, between one breath and the next, the listener begins to feel it too. The quiet gravity of existence, the gentle rhythm of the cosmos, the endless calm that has always been there, surrounding everything, soft as dust, luminous as memory, infinite as sleep.